Great, we are good to go. So, Homan is going to be the next speaker. Thank you very much.
All right, thank you, Dave. Hello, everyone. First of all, I would like to thank the organizers for inviting me to give this talk and for making this hybrid conference work so well. Today, I will give an overview of NICER observations of black hole X-ray transients. I will start with a brief overview of NICER and compare it to RXTE, which was our previous black hole transient machine. I'll give a brief overview of black hole X-ray binaries that NICER has observed so far. And the main portion of this talk will be a presentation of science highlights. I'll try to cover as much ground as possible, which means that most results will not be discussed in detail. NICER stands for Neutron Star Interior Composition Explorer. It is an international space station payload that was launched on June 3rd, 2017. You can see it here sitting on the space station. It consists of 56 concentrators coupled with silicon drift detectors that are sensitive in more or less 0.3 to 12 keV band. And you can see the instrument here up close. 52 of the detectors are currently functional. And the main science goal of NICER is the study of neutron stars through timing in the soft X-ray band. However, NICER's instrument properties are also great for studying a wide variety of other X-ray sources, including black hole X-ray binaries. NICER shares many properties with RXTE, which was a very successful mission for black hole X-ray transients. It offers high time resolution, can handle the high X-ray fluxes observed near the peak of outbursts, and it typically has a very flexible observing schedule, allowing for rapid follow-up of transient events. However, NICER differs from RXT in a few key areas. It has lower background, allowing us to follow sources to significantly lower fluxes. It has a very different bandpass, much lower than RXT. And this is great for studying the thermal components in X-ray spectra, but it is less optimal for QPOs, for example, since these increase in strength with energy. And finally, it has a much better spectral resolution than RXT, which is great for studies of broad iron lines and wind features. All in all, this means that NICER is great for monitoring black hole X-ray transient outbursts, while also providing a different perspective than RXT. Here is a hopefully complete list of all black hole X-ray binaries that have been observed with NICER. Only 6 are persistent sources, while the others are all transient systems. And of those transient systems, the majority are systems that were actually discovered in the last couple of years. 3 of these new transients became very bright. The first one was MAXI J 1535, discovered in 2017, which showed these beautiful reflares at the end of its decay. The next bright one was MAXI J 1820 plus 070, discovered in 2018, which until recently was the brightest black hole observed with NICER, and which has shown several minor outbursts as well in the last few years. And finally, MAXI J 1348, which was discovered in 2019 and almost became as bright as 1820. As you can see, all 3 had outstanding coverage with NICER. And also due to NICER's relatively low background, especially compared to RXTE, we were able to follow the sources over a very large range in count rate. And all 3 sources will be discussed in more detail later on. Here are light curves of some of the fainter transients. The number of new black hole transients really has been unusually high in the last couple of years, and we've been extremely lucky in that respect. And here are 3 very recent transients. 4U 1543 became extremely bright, but was already in the soft state when NICER started observing. MAXI 1803 showed periodic absorption dips at about 7-hour intervals early on its outburst. And here in green is AT 2019 Way, which may or may not harbor a black hole, but has been in outbursts for more than a year now, which is quite unusual. I'll continue with a selection of highlights from the observed transients. Let me start with 1535. This source was discovered soon after NICER started its science operations. And here on the left is a figure from Cuneo et al. Showing the NICER light and hardness curve, and at the bottom is Swift light curve. And it's good to see how well NICER performs at these relatively low fluxes compared to Swift, despite not being an imaging instrument. There are a couple of highlights I want to discuss. First is the fact that 1535 remained in a soft state down to a very low luminosity at about an Eddington fraction of 2 × 10⁻⁵. This is much lower than normal. Typical soft to hard state transitions occur around 1% of the Eddington luminosity. So this is really much lower. Soon after this transition, the source started showing reflares, which can be seen here, during which the source transitioned between the hard state and intermediate states. And here are spectra from the valley of these reflares and the peaks, and you can see a clear change in the spectral shape. These transitions resulted in hysteresis loops in the hardness intensity diagram, which is shown here on the lower right. And this looks similar to what is seen for major outbursts. However, these transitions between the hard state and the softer states occurred at the lowest luminosities observed so far for a black hole transient. This suggests that the same physical mechanism responsible for hysteresis loops in major outbursts can also work at lower luminosities. 1535 also showed strong iron lines near the peak of its outburst. And these were studied by Miller et al. A broad component can clearly be seen here on the left in the residuals of a continuum fit to the spectrum. And based on this broad component, Miller et al. Argued that the source likely harbors a near maximally spinning black hole. However, they also detected a weak narrow component to the iron line, likely produced farther out from the black hole and suggestive of a warp in the accretion disk. Next, some QPO stuff from MAXI J 1348. Well, as you probably know, there are several types of low frequency QPOs in black hole X-ray binaries. And of these, the type C are the most common. And the type B QPOs are relatively rare. But MAXI J 1348 turned out to show them very regularly near the peak of its outburst. Here on the left, I show NICER and MAXI light curves and hardness curves of 1348 from a paper by Zhang et al. And the blue dots here show or indicate the observations with type B QPOs. And also in the hardness intensity diagram and RMS diagram, they are shown in blue and they show up in the locations where we would expect them for type B QPOs. We already know that type B QPOs can appear and disappear quite rapidly. And this was also the case for 1348. This can be seen from these figures. Here on the left are light and hardness curves, with red indicating segments with type B QPOs. In the middle panel, we see the same light curve but with the time gaps removed. And here on the bottom, a dynamical power spectrum, clearly showing that the QPO switches on and off. And on the right are time averaged power spectra for segments with the QPO in red and without the QPO in black. And here is another example with the QPO switching on here in the second part of the observation. Although it was already clear from RxDE data that the appearance of type B QPOs was related to changes in the high energy tail in the spectrum, the role of the accretion disk could not be studied as well due to RxDE's bandpass. And with NICER, this is now possible. In the middle panels here, spectral ratios are shown with the type B QPO spectrum divided by the non-QPO spectrum. And clearly, as can be seen here and here, the spectra with the type B QPO have a much stronger hard tail. A detailed spectral analysis of 4 of such observations shows a strong anti-correlation between changes in the comptonized flux and the disk flux, as shown here on the right. The larger the decrease in the disk flux, the larger the increase in the hardtail. And this strongly suggests a redistribution of the accretion energy between the accretion disk and the comptonized component as the type B QPO switches on and off. Zhang et al. Also found that the increase in the hardtail is likely due to an additional comptonized component, possibly from a jet. And the presence of two comptonized components was also hinted at by a detailed analysis of the type B QPO, RMS spectra, and phase lags. Garcia et al. Tested both a single comptonization model, here on the left, and a dual comptonization model, here on the right, which consists of two connected and interacting components, for example, a corona and a jet. It is clear that the double comptonization model here on the right performs much better. And you can also see how crucial the NICER coverage below 3 kV is for distinguishing between the two models. Here is a result from one of the lesser known transients, MAXI J0637. It was already well known that in the soft state of black hole X-ray transients, the flux of the disk component is proportional to the inner disk temperature to the 4th power, which suggests a constant inner disk radius. For intermediate states, and especially the hard intermediate states, this was harder to study with RXT due to the lack of low energy coverage. As can be seen from this plot on the left from a paper by Jana et al., NICER observed 0637 in the soft intermediate state, the soft state, the hard intermediate state, and finally the hard state. And good constraints on the disk properties were obtained for the first 3 states. This can be seen here on the right. Jana et al. Found that the flux and temperature closely followed the expected T to the 4th relation, here shown as a black line in the soft state, represented here by the blue points. However, this relation also seems to extend to the 2 intermediate states, suggesting very little movement in the inner disk radius between these 3 states. Next is GRS 1915, which was discovered in 1992 and has been in outburst ever since. It is, of course, known for its exotic variability modes and powerful jet ejections. And as can be seen from these long-term light curves, in 2018, the source entered a long historic minimum, and it appeared it was finally returning to quiescence. Here is the NICER coverage of 1915. As you can see, NICER observed the source very regularly since launch. Joey Nielsen wrote a nice paper about wind signatures in the NICER spectra taken during the bright phase here, which he may talk about on Thursday. And on Wednesday, Edward Nathan will talk about phase-resolved QPO spectroscopy using NICER and NUSTAR observations taken around the time indicated with the red dot. NICER also supplied us with great coverage of this extended minimum. And just when it looked like 1915 was starting to brighten again, in May of 2019, the source flux plummeted, and it entered a phase in which it showed highly erratic behavior, as is clear from these light and hardness curves. We now understand that 1915 is in an obscured phase, as was shown by Miller et al., for example. NICER provided us with a front row seat of the transition into this obscured state. Here are figures from a paper by Koljonen and Hovata, and the upper panel shows the evolution of the flux, with the long extended minimum, the small recovery, and then the transition into the obscured state. They selected 7 observations, here labeled A to G, for which they show the continuum evolution here on the left and the evolution of the iron absorption lines here on the right, with the colors matching between the panels. As the count rates dropped, we see that at low energies, the flux hits a base level, while at higher energies, the flux continues to decrease. But it's especially the transformation from absorption lines into emission lines that is really quite striking. Without going into detail, What this tells us is that most of the soft flux from the central source is obscured. And what we see is probably mostly light scattered into our line of sight by an extended accretion disk corona, which is also responsible for the emission lines. During the obscured phase, 1915 occasionally also showed very strong flares, and the higher count rates during these flares allows for a more detailed study of the obscuring medium. Here are figures from a paper by Nielsen et al. In which one of these flares was studied. The spectra shown in the lower left correspond to the similarly colored segments of the flare light curve. And the evolution that we see shows similarities to that seen during the transition into the obscured state, which I showed on the previous slide, with emission lines here transforming into absorption lines at higher count rates. Well, modeling of these spectra suggests the presence of various ionization zones with different densities. And depending on whether the ionizing radiation is absorbed or unabsorbed, different cartoons of the obscuring material can be drawn, in which the radial distributions of the ionization zones are quite different. Well, regardless of the nature of the ionizing flux, it is clear, though, that much of the absorbing material is located far out in the accretion disk, close to the outer radius. But what causes such a massive amount of obscuring material in the outer disk remains unknown, however. In addition to several strong flares, there have also been a few periods in which the flux increased for several weeks or longer. During these periods, 1915 would often show some of its classic variability states, which I show a few examples of here. And they suggest that despite the source being heavily obscured, the central source is still doing its thing and is definitely not asleep. And Arash Baramian will talk about the obscured state of 1915 in more detail tomorrow morning. Now the final source, MAXI J 1820 plus 70. 1820 was discovered in March 2018 and became one of the brightest black hole X-ray transients in the last 20 years. More than 750 NICER reportings were made of the outbursts, covering more than 5 orders in magnitude. A lot of interesting work has been done with the NICER data from this source, but I only have time to discuss a few results. I'll discuss results from the hard state, the hard to soft transition, and the soft state. I'll start with the hard state. These are results from an analysis by Aaron Kara et al. They selected a set of observations throughout the hard state and try to understand the evolution of the accretion flow this way. Note that color coding will stay the same in all the figures that I'll show next. First, they looked at the evolution of the iron line, which shows both a broad component and a narrower component. While the broad component stayed the same over time, the narrow component became weaker with time, and the latter probably means less X-ray reflection from large radii, while the former indicates a nearly constant inner radius. Next, they looked at phase lags. They found that the soft lags, which are due to thermal reverberation and which show up as the negative parts here in these phase lag curves, shifted towards higher frequencies, which is shown here. Well, this combined with other results from their analysis led to this cartoon of a corona that shrinks with time while the inner accretion disk radius remains more or less constant. J-Lag et al. Also analyzed hard state observations, but with a focus on power spectral components. They identified 4 broad Lorentzians in the power spectra, shown here on the left. And each of these Lorentzian components had a different spectral dependence, as shown here in the upper right. For example, the highest frequency component also had the hardest X-ray spectrum.
You've got
Well,
5
from
minutes
their
left.
analysis, they found that the spectra are well modeled by a disk black body and thermal comptonization, but that the presence of at least 2 comptonization zones with different temperatures and optical depths are required. And that's illustrated here in the simple cartoon with the 2 comptonizing zones labeled with Roman numerals 2 and 3, also having a very different energy spectrum. Wang et al. And DeMarco et al. Both used reverberation lags to study the evolution from the hard state to the hard to soft transition. And like Kara et al., they both find a trend of soft lags shifting to higher frequencies. But this trend reverses during the transition, as can be seen here. The yellow curve is the end of the hard state, whereas during the transition, this soft lag becomes lower in frequency. This is probably the result of a suddenly expanding corona. This reversal in the trend of the soft lag occurred a few days before a jet ejection, suggesting that this coronal expansion and the jet launch may be connected. Note, by the way, that in their cartoons, the 2 papers differ on the behavior of the inner disk, which is more or less constant here on the left, but moves inward here in the right cartoon. Jingji Wang will perhaps address this in her talk tomorrow morning. There's also a poster by Barbara DeMarco on her work. Well, as I just mentioned, 1820 made a hard to soft state transition during which a jet ejection took place. And in the next slide, I zoom in on the phase of the transition that is marked here by the 2 red lines. Here are plots from a paper by Wood et al. The 3 middle panels here show light curves in various energy bands going from low energies to higher energies, and a very sharp jump in count rate is seen here. In the dynamical power spectrum, in the bottom panel, we see a type C QPO increasing in frequency together with its harmonic, slowly getting weaker, and then suddenly, right at the jump, a type B QPO appears. This is a little clearer in this picture, where the time gaps are removed. You see the type C QPO here with the harmonic increasing in frequency, but weakening, and then suddenly, right at the jumping count rate, a type B QPO appears. And these are the corresponding power spectra from before and after the jump. Now back to the figure from Wood. In the top panel is a radio light curve showing a strong radio flare occurring just after the QPO transition. Analysis of VLBA data, shown here by Wood et al., revealed fast and slow ejecta. And proper motion studies show that the slow ejecta were launched about 2 hours before the QPO switch. And that period is marked here with purple lines in the figures. And these slow ejecta are also responsible for the radio flare, shown here in the upper figure. This is highly suggestive of a connection between the appearance of the type B QPOs and jet ejections. However, I will also note that there is no clear X-ray signature of the fast ejection, which took place around the time of the green lines here. This is my last science slide, a fun result from the soft state by Fabian et al. They analyzed simultaneous NICER and NUSTAR spectra of the soft state and found that in addition to a disk component here, low energies, and a hardtail at high energies, an extra thermal component was required, peaking around 3 to 4 keV. This emission was interpreted as possibly coming from matter that has just entered the plunge region inside the innermost stable circular orbit, where matter begins to fall freely into the black hole. Finally, I want to make a few small remarks about data analysis, observing time, and the NICER community. First of all, development of NICER analysis software is still ongoing. The most recent HEASoft release includes much improved tools, which allow for easier tracking of the number of active or selected detectors. Custom response and ancillary response files can also be created with new tools. And background modeling and software is still improving as well. And tools are publicly available through the NICER website. We had 3 guest observer rounds so far, and the deadline for cycle 4 is on November 10. And like for cycle 3, there is the option for joint NUSTAR time. I will also point out the availability of DDT time. The NICER team has been quite generous with this, so please don't hesitate to apply. And finally, since April, there is a NICER users group that represents the NICER community. I'm one of the members. If you have any concerns, questions, or suggestions related to everything NICER, please feel free to email us at the highlighted address here. This is the end of my talk. I'm happy to take questions.
Thanks a lot, Jeroen. That was a great talk. Are there any questions, please? So far, I don't see any in the Zoom. So any from the audience?
No, no question here. Apparently, oh, yes, one.
I have rather a technical question because you presented.
Can you just say who you are, please?
Special
Oh, yes.
type of sources. Do you think NICER can observe lags for ULXs?
Ooh, I don't know. I'm not a ULX expert. I don't know if it's been tried. Yeah, I don't know how to answer that question.
Okay, sorry, I know it was technical question.
Yeah.
Any other questions, please? Federico Vincentelli.
Hi, very nice summary. I wanted to know if there is a minimum time for which, let's say, for how long NICER will be operating. What's the minimum time?
So, sorry, can you repeat?
How long will the mission last for as minimum?
I'm not sure exactly. It's coming up for a senior review later this year or early next year. I think it's good now, probably until the end of 2022. But I think they're hoping to extend it by a couple more years.
Okay, thank you very much.
Dave, there's a question in the chat.
Oh, yes. Hemanth says, can you please elaborate the comment about NICER being bad at detecting QPOs, and how well is the energy to channel calibration done in the instrument?
Well, it's not necessarily bad at QPOs. I mean, I've shown several QPO detections during during my talk, but the point is QPOs tend to increase in strength with energy, and NICER's response peaks at 2 keV. So that is just not optimal. But we've been lucky that there have been a few very, very bright transients, so that makes up for the limited sensitivity at high energies. And about the energy to channel calibration, yeah, I'm not an expert on this. I can't really tell. It's been improving, but yeah, that's all I can say.
Thanks. And there's a comment in the Slack by Philip Lee, who says, lags have been seen for ULXs with XMM Newton, so it should be possible for NICER. Okay, so are there any other short last questions? Javier Garcia?
Yeah, I'm not sure this is a fast question, but I was thinking about when you talk about the type B QPOs and that there seems to be this tail at high energies. I was wondering how much of how confident are you that this is a real correlation? Because you're comparing two observations and two different times. So could it be that just, comparing QPO versus non-QPO is just normal standard variability of the power law component and is not necessarily connected to the QPO?
Well, I mean, we definitely see a big jump in the hardtail at the time when the QPO switches on. Is that what you meant?
Yes.
Or are you...
Yes. I guess the better question is, you show just two observations when this happens. Is this seen consistently through many observations?
Yes, I think there were 4 observations in total for which this has been seen in one source. But I mean, there are more sources with type B QPO, so we could, probably expand that to a larger set of observations.
Thank you.